Hey science students, and welcome back to another lesson with me, Leslie, from Tesla Tuition Videos. Today we are working on the chemistry topic of polar and non-polar bonds. Let's get started. Okay, so polar bonds are not the same thing as polar molecules. And in a similar way, non-polar bonds are not the exact same thing as non-polar molecules. Let's first just take a little step back and make sure we have some background info for today's lesson. So chemical bonds are the bonds that hold together the atoms within a molecule, which is something that contains two or more atoms chemically bonded. Now, intra as a prefix means inside of, as opposed to inter, which means between. So intramolecular forces are inside of a molecule between atoms. But between atoms can also be described as interatomic. Now, in this topic, we are also focusing mainly on a specific type of chemical bond called the covalent bond. Covalent bonds is the sharing of at least one pair of electrons by or between two non-metal atoms. You will come to see that non-metal atoms, they share their outermost valence electrons with other non-metal atoms in an effort to try and fill their outermost energy levels, which is a stable condition or state to be in. Now, each covalent bond consists of a pair of shared electrons between two non-metal atoms. Now we're going to have a look at different types of covalent bonds, namely polar covalent bonds and non-polar covalent bonds. Now, in order to determine if a covalent bond is polar or non-polar, we have to consider something called electronegativity. This is the definition of electronegativity. It is a measure of the tendency of an atom to attract a bonding pair of electrons. Now, in my own words, I would describe electronegativity as how much a bonded atom attracts or pulls a shared pair of electrons towards itself. Now, you'll see that on periodic tables, there tends to be a key showing you what the information is for each element. Now, they show you here that the number written down the side, that is electronegativity. So all these little numbers written going down the side here, they are electronegativity. For example, the electronegativity of oxygen is 3.5, and the value of electronegativity ranges from 0 to a maximum of 4, and electronegativity values do not have a unit. And we will be using various elements' electronegativity values when we now determine whether the covalent bond between atoms is polar or non-polar. Right, so starting with non-polar covalent bonds. A non-polar covalent bond is an equal sharing of electrons. Now, in my own words, I would say that a non-polar covalent bond consists of electrons being shared equally or evenly between two bonded atoms that have equal values of electronegativity. So if both bonded atoms have an equal attraction for the shared electrons in the covalent bond, then it will be a non-polar bond. The electrons will be shared perfectly equally and sit exactly in the middle between these two atoms. To help us figure out if bonds are polar or non-polar covalent, we use something called electronegativity difference, which is just usually symbolized as delta or triangle En, difference in electronegativity. I've written here in purple in the corner, note, to get difference in electronegativity or delta En for a certain bond, all you have to do is subtract the smaller value of electronegativity from the larger value of electronegativity for two bonded atoms. But for non-polar covalent bonds, it's really the same number subtracted by itself. For non-polar or pure covalent bonds, delta En, the difference in electronegativity, is exactly equal to 0. That's how you know it's a non-polar covalent bond. Let's take a look at a couple of examples. Right, so examples of substances that have non-polar covalent or pure covalent bonds would be diatomic molecules. Remember that diatomic molecules consist of molecules that have two atoms of the same element bonded together, and we actually have 7 diatomic elements. I've shown some of them here. N2, that's nitrogen, Br2, bromine, O2, that's oxygen, H2 is hydrogen, Cl2 is chlorine, and then the other 2 examples would be iodine, I2, and fluorine, F2. These are our diatomic molecules, and they all contain non-polar or pure covalent bonds because the atoms of the same elements have the same electronegativity, so difference in electronegativity is 0. Now, before we look at an example, I've just given a tip here in red that when you are finding out if a bond is polar or non-polar, you should first draw the Lewis diagram. So the Lewis diagram, please make sure you know how to draw those. They're often asked for marks in tests and exams. And here it will be a useful place for us to label our electronegativity values for each atom. So for my example here is nitrogen N2. Nitrogen is actually in group 5 of the periodic table. It has 5 valence electrons. Let's start with our first nitrogen atom, which I'll represent the electrons for using dots. The other nitrogen atom, I will use crosses to represent the electrons. So here's my first nitrogen atom, and I'm going to try and eventually put the 2 nitrogens next to each other with their lone pairs on opposite sides. So 1, 2, 3, 4, 5. That's the 5 valence electrons. And the 3 unpaired valence electrons are going to pair up with the 3 unpaired valence electrons of the other nitrogen atom. So now here's the other nitrogen atom, and here is its 5 valence electrons. 1, 2, 3, 4, and 5. Okay, now the unpaired electrons are going to get together and form pairs so that now the final structure is going to look a little bit different. So I'm going to erase all those unpaired valence electrons quickly, right? And now they're going to form a triple covalent bond in between these two. And I should try and draw these shared electrons exactly in the middle between the 2 nitrogens because they're being equally shared in a non-polar covalent bond. So here we go. Here's 1, 2, 3 pairs of shared electrons between the 2 atoms. Right. So now we want to know if the bond is polar or non-polar covalent. So I look on my periodic table for the electronegativity of nitrogen, and it is 3, 0. And I'm going to label it beneath each of these atoms. 3, 0, 3, 0. Now I work out the difference in electronegativity, delta En. And although there's 3 covalent bonds, I only work it out once for each type of bond. So now delta En is going to be, it's just, in this case, I can't say bigger minus smaller number. It's the same number subtracted by itself. So it's going to be 3, 0 minus 3, 0. And that gives me an electronegativity difference, delta En, equal to 0. Okay. Now that is our reasoning for saying that the bond is now a non-polar covalent bond or pure covalent bond. So bond is non-polar covalent. As soon as your difference in electronegativity for 2 atoms is 0, the covalent bond between them will be a non-polar or pure covalent bond. This is true for all our diatomic molecules, and there are 1 or 2 other substances involving elements that have equal electronegativities as well. Now let's move on to our polar covalent bonds. Right, so onto polar covalent bonds. Now, a good description of a polar covalent bond is an unequal sharing of electrons between atoms. Now, in my own words, a polar covalent bond is the unequal sharing of electrons between atoms of unequal electronegativity values. Now your two bonded atoms do not have equal electronegativities, and that is going to result in a polar covalent bond where the electrons are not being evenly or equally shared. In fact, you'll find in this case that the shared electrons are going to sit closer to the atom that has the higher electronegativity or attraction for those atoms. Right. Now, the important thing to realize is that in order to have a polar covalent bond, your difference in electronegativity, I realize I forgot a little N here, let's stick it in there. Your delta En for polar covalent bonds is never equal to 0. It's always a value other than 0. That's how you know that it will be a polar covalent bond, because the difference in electronegativity of the bonded atoms is a value other than or not equal to 0. Okay, let's have a look at a substance that will end up having polar covalent bonds. Now, there are so many examples of substances with polar covalent bonds. For our example, though, we're going to do HCl, which is hydrogen chloride, also known as hydrochloric acid. Now you'll see that I've already preemptively drawn the Lewis diagram. Here's hydrogen. The dot represents the single valence electron of hydrogen. And chlorine, which is in group 7, has 7 valence electrons, one of which is unpaired, and it pairs up with the single unpaired electron of hydrogen to make a single covalent bond. Now, you can draw the covalent bond, which is really a dot and a cross, 2 shared electrons. You can draw the 2 electrons vertically or horizontally. It does not matter. Right, so now the Lewis diagram will be a place where I can label electronegativity values, and I have my periodic table with me. So for hydrogen, the electronegativity value is 2,1. I'll just add it here underneath. And for chlorine, it is 3,0. Remember, electronegativity values do not have a unit. So now let's work out the difference in electronegativity, delta En. There's no official formula, you just jump straight to the substitution where you take the larger value minus the smaller value. So 3,0 in this case minus 2,1. That's going to give us an answer of 0,9 for my difference in electronegativity. Now, as soon as your electronegativity difference is not equal to 0, which it isn't in this case, it is 0,9, so not equal to 0, that tells us these bonds are polar covalent. Right, let's add our conclusion over here. So as soon as the electronegativity difference is not equal to 0, the bonds are polar covalent. All right. Now, especially for government school learners, but sometimes also for private school learners, they might distinguish between weak polar covalent bonds and strong polar covalent bonds. Now, we'll put this up on the screen, but generally speaking, if you get an electronegativity difference that is between 0 and 1, not equal to 0, then that's considered to be a weak polar covalent bond. For example, an electronegativity difference of 0.4, for example, might be considered a weak polar covalent bond. Now, if your electronegativity difference is between 1 and 2.1, that's considered to be a strong polar covalent bond. If your electronegativity difference is bigger than 2.1, then your covalent bond is so polar, the electrons are being shared so unevenly that they're essentially being transferred from one atom to another atom. And that's what we call an ionic bond. Ionic bonding is an extremely polar bond where the electrons are not shared anymore, they're transferred from one atom to another. We must remember that not all molecules with polar covalent bonds end up being polar molecules. But it was true that all molecules with non-polar covalent bonds, they will end up being non-polar molecules. That brings us to the end of today's lesson on polar and non-polar bonds. Head over to our website for our full-length science videos.